right. So this is a bad loss, right. So basically what I am saying is that the light blue curve is a bad way to approximate the dark blue curve. So we need a better ways to do this. Let us see if there are better ways to do this. Okay. So for towards that, let us start maybe examining the support vector machine algorithm. So if you remember the support vector machine algorithms formulation, the soft margin support vector algorithms formulation, it was minimized over W and psi half norm W squared, which is a proxy for the margin, plus sum over I C times sum over I equals 1 to n psi I, such that W transpose xi into yi plus psi I is plus psi I is greater than or equal to 1 and psi I is greater than or equal to 0. This was the formulation. We came up with this formulation after detailed discussion about support vector machines. Now, one way to rewrite this formulation would be as follows, because we want to understand this from a loss functions point of view. I can rewrite this as equivalently, minimize over W and psi. I am not doing major modifications here. I am going to bring it in some standard form. I want to understand this psi I better, right. So, psi I is greater than or equal to 1 minus W transpose xi yi and psi I is greater than or equal to 0. Now, which means that if I put these two things together, then it means psi I is greater than or equal to 0, or epsilon I, right. So, epsilon I is greater than or equal to 0. Epsilon I, remember, is the bribe that the data point I pays, or the slack variable, to get to the right side of the line, right. So, that should be greater than or equal to 0 and it should be greater than or equal to 1 minus W transpose xi yi, which means that it should be greater than or equal to the maximum of 0 comma 1 minus W transpose xi yi, right. So, so equivalently I can write this as half norm W squared plus C times sum over I is 1 to n psi I, where psi I is greater than or equal to this. Now, this is equivalently, I can write this as equivalently minimize over W half norm W squared, right. So, remember the bribe that you will pay is either 0 if the W actually correctly classifies your xi with margin 1 or you will exactly pay 1 minus W transpose xi y. You won't pay extra unnecessary bribe, right. So, which means that this can be written as C times sum over I equals 1 to n. Well, psi I is at optimality, psi I is going to be like exactly the maximum of 0 and 1 minus W transpose xi yi, which means that I can directly write this as max over 0 comma 1 minus W transpose xi yi, right. So, this is an equivalent formulation where I am just trying to find the W in RD such that you have some term here which the motivation for this was maximizing the margin plus some other term here. Now, remember this term depends on data, right. So, data dependent term. Why? Because the xi and yi appears only in this picture here, whereas this is model dependent, right. So, this depends only on W that we are trying to learn. Now, we can now view this as if this guy is a regularizer. If you remember from ridge regression, we had a loss function which is a squared loss and then we added half norm W squared as a regularizer. Now, this half norm W squared serves the same purpose, right. So, there it was a lambda by 2 norm W squared, but then that lambda effect is got using the C. Somehow, we were trying to balance two terms using a lambda. Here that balancing happens on the other side, but that does not really matter. You can bring it this side as well, right. So, now this half norm W squared is the regularizer. Now, this data dependent term is the loss, right. So, this is the loss, how much loss that a particular W suffers on my data set. Now, in our notation, right, so this W transpose Xi is what we are calling as G of Xi, right. So, this is in general, this could be any G. If it is linear, then this is W transpose X, which means that what is exactly the loss that we are learning? Well, now let us go back and see how this loss fits into our picture of original picture. Now, remember, this is the picture that we had, where we had this 0 1 loss, 0 1 loss. We also had squared loss, which was G of X minus 1 squared. This guy is G of X into Y. This is my loss. Now, I want to understand the SVM's loss. SVM's loss looks like the following: max of 0 comma 1 minus G of X into Y. So, this is the loss per data point. Now, that loss is summed up over n different data points, right. So, for a single data point, it is max of 0 comma 1 minus W transpose X into Y, which is G of X into Y, right. So, remember, the most important thing is that this loss depends on the product, right. So, of whose once you learn the W using this product, then you will find the sign of this to make a prediction. Okay. So, now how does this picture look like, right. So, as a function of G of X into Y, if you think of this as a variable, now max of 0 comma 1 minus that variable, let us call that Z, right. So, if this was Z, so this is just max of 0 comma 1 minus Z. So, how does that picture look like here? Well, 1 is somewhere here, this is 1, this is where this guy becomes 0, the squared loss becomes 0. So, this is 1, so this is where the 0 1 loss takes value. Now, if my G of X into Y is greater than 1, now what would happen? Well, 1 minus G of X into Y will become less than 0, because if G of X into Y is greater than 1, so that will be a negative value. So, the max of 0 comma negative value will be 0, which means that if it is anything greater than 1, is going to get a 0 value, right. So, there is no loss. On the other hand, if G of X into Y is less than 1, that is, we make a prediction with margin less than 1 in the SVM's interpretation, then we suffer a loss which is max of, it is never going to be 0, because if G of X into Y is less than 1, so 1 minus this is always going to be positive. So, you are always going to suffer a positive loss, so it is not going to be 0. So, 1 minus Z is just a linear function, right. So, it's going to look something like this, especially when G of X into Y is 0, this value will be 1. So, which means that at 0 this will be 1, and then at 1 this will be 0, and this will be a linear function, right. So, this is a line. Okay, maybe I should draw this carefully. Yeah, so this is a line, and at 1 it becomes 0, and then it continues to say 0. Now, as you can see, even if G of X into Y is a large positive quantity, the loss that I get is still 0, whereas in squared loss it kind of started increasing, because we are essentially, that is tuned for a regression problem, whereas this loss is tuned for a classification problem. On the other hand, it is still not the same as the 0 1 loss. Of course, it cannot be the same as the 0 1 loss. Now, what you can think of is, right, so the nice property of the orange line, which is the SVM's loss, is that it is in some sense the best convex approximation of the 0 1 loss. You can think of it that way, right. So, this orange line is a convex function of G of X into Y. The blue line is, the light blue line is also a convex function, but then it is not a great approximation for the dark blue line. On the other hand, the orange line is a convex function, which is why solving the problem is easier, and is also a good approximation for the dark blue line, right. So, and that is why this performs much better than just using a regression problem to solve classification, right. So, this loss has a name in literature. So, this loss is called as the Hinge loss, right. So, this is called as the Hinge loss. Basically, now you can view your SVM problem itself as if it is solving a hinge loss. It is trying to find a W which minimizes a hinge loss plus regularization. like how the ridge regression was solving a squared loss plus regularization, L2 regularization. Now SVM can be thought of as solving, minimizing the hinge loss plus L2 regularization, right. So the regularizer, of course we can play around with the regularizer as you wish, but then if you want good easy solvability, then using an L2 regularizer typically helps. And hinge loss is basically trying to approximate the 0-1 loss, so that you get rid of the NP hardness somehow. Good. So now we have put two different algorithms in the same perspective. Let's go ahead and see if we can put other algorithms also under this perspective, right. So that kind of will give us a feel for how different algorithms are different with respect to dealing with the NP hardness problem. Okay. The next algorithm that which is another popular algorithm that we have seen is the logistic regression algorithm. So what was the logistic regression algorithm's problem? Well, we were trying to maximize a likelihood problem there, where we assumed that P of y given x is some logistic function on W transpose x, right. So if you remember this from our discussion of logistic regression, we were maximizing the likelihood function over W, where we had product of I equals 1 to n, because the points were assumed to be IID, the labels. So now we used, let's say, some sigma of W transpose xi, which sigma is the logistic function, power zi into 1 minus sigma of W transpose xi power 1 minus zi, right. So where sigma of z, sigma of a is 1 by 1 plus e power minus a. This was the logistic function that we used, and zi, in this case I am using zi instead of yi because zi was 0 or 1, but then the way we are trying to deal with the losses here is with yi as 1 or minus 1. So we need to kind of map this to the 1 or minus 1 world a little bit later, right. So zi is 1, the label is 1 if yi is 1 plus 1, and zi is 0 if yi is minus 1, right. So because there when we discuss logistic regression, we assumed that the labels were 0 or 1, and that is why this formulation came about. So now just to note that, I mean, we can treat the data set as having labels as plus 1 or minus 1, just that there is a direct relation between zi and yi which we need to use. Okay. So what does this give us? Well, this gives us, so this is the likelihood function. We then take the logarithm of this, and then we will say that we will maximize over W, sum over I equals 1 to n, zi log sigma W transpose xi plus 1 minus zi log 1 minus sigma W transpose xi, and then we looked at its gradient and all that when we were discussing logistic regression. This is equivalent to minimizing over W, sum over I equals 1 to n, zi rather minus zi log sigma W transpose xi. I am writing this as a minimization problem because we want to understand everything as a minimization problem with respect to some parameter of interest, in this case W, and then see what is the loss function that comes about, right. So plus zi minus 1 log 1 minus sigma W transpose xi. Okay. Now let us see, so this is the loss over n different data points that we have. Now let us see what is the loss for a single data point when let us say zi equals 1. Of course, there are two cases, zi can be 1 or minus 1. Let us say when zi is 1, now what happens? If zi is 1, then this is the contribution of the loss of ith data point, but then if zi is 1, the second term is 0. So that does not contribute. This guy is 1, so which means that this value is just minus log of, let me write this in the same color, is minus log of sigma W transpose xi, right. So because this is 1, assume if this is 1, then this is the contribution, which is just minus log of what is sigma of W transpose Xi, which is just 1 plus e power minus W transpose Xi, which is log of 1 plus e power minus W transpose Xi. Now, if Zi is 1, that also means that in our notation Yi is plus 1, right. So, which means that I can equivalently write this as log of 1 plus e power minus W transpose Xi into Yi, right. So, it is the same thing. Basically, what I am saying here is that for every point in the data set where the label is 1, now the loss of a particular W that you want to choose with respect to that data point can be written like this, right. Similarly, what happens when loss is loss for a single point when Zi equals 0. Zi equals 0 in our notation is Yi equals minus 1. Zi equals 0 would mean what? So, again let us go back to the loss. Well, if Zi is 0, the first term does not contribute anything, only the second term contributes. If the second term, what does it contribute? It contributes minus 1. So, it contributes minus log of 1 minus sigma of W transpose Xi, which is minus log of 1 minus 1 by 1 plus e power minus W transpose Xi. This is just algebra, nothing major going on here, which is minus log of, if you play around with this, you will get that this is just e power minus W transpose Xi by 1 plus e power minus W transpose Xi, which is equivalent to minus log of, let us say what I do here is I divide both the numerator and denominator by e power minus W transpose Xi divided by, I can do that because it is always going to be a positive term, it will not be negative. So, sorry 0. So, division is still okay. The reason why I am doing this will be apparent in a minute. So, this numerator will become 1, the denominator will become, you know, the first term will be e power W transpose Xi and the second term will be 1. So, now this itself can be written as log of 1 plus e power W transpose Xi. This is also same as log of 1 plus e power minus W transpose Xi into Yi. Why? Because now we are looking at the case where Zi is 0, which means Yi is minus 1, which means that W transpose Xi can be written as minus W transpose Xi into Yi. This is minus, Yi is also minus 1, right. So, I can write it like this. Now as you can observe that in both the cases, I have managed to write my loss for a single data point as exactly the same thing, depending on log of 1 plus e power minus W transpose Xi Yi, which means, what does it mean? It just means that my logistic regression can be equivalently thought of as, right. So, equivalently minimizing over W sum over I equals 1 to n log of 1 plus e power minus W transpose Xi Yi, right. So, if I have the data set, if I represent my labels as 0 and 1, then I would rather write this as in this way, right. So, that would be the logistic functions probability of the maximum likelihood formulation, or if I represent it as plus 1 minus 1, then I can simplify it and put it in this way. Both are exactly equivalent because the loss with respect to every data point depends on whether Y is plus 1 or minus 1 or Zi is 0 or 1, and then we just derived that in both the cases you can represent the loss contribution of the data points to the loss can be written in this form. Now, this helps us because now what we have done is we have written it in terms of W transpose Xi into Yi. Now, this is just our G of X in Xi into Yi, which means that we can put this guy now in the picture that we already have, right. So, earlier it was not possible. Now, because we have written it this way, we can put it in our picture of loss for a single data point. Let us do that and see what comes out, right. So, again just to refresh, I mean it is good thing to refresh these things, especially if you are seeing it the first time. We have the 0 1 loss as usual, maybe not too high, yeah. we have we saw the squared loss and we also saw the hinge loss. Now, okay, so let me put this all right. So, this is g of x into y minus 1 squared loss 0 1 loss, indicator of g of x not into y less than 0, hinge loss max of 1 minus g of x into y comma 0. Now, we have the fourth loss, which is the logistic regressions loss, which is log of 1 plus e power minus g of x into y, right. So, this of course, the x axis is g of x into y, the y axis is loss. How does this look like in this picture? Well, this is another way to deal with our NP hardness. How does this look like in the picture? Well, I may not be able to draw it to scale, but then if I do a reasonable approximation of this, this kind of goes down like this, right. So, it never becomes 0, of course, because you have a 1 plus log of 1 is 0, but then log of 1 plus something, which is never going to be 0 because it's e power something. So, this loss is never 0, but then it keeps getting lower and lower as g of x into y increases, right. So, and this is another way you can think of as dealing with the NP hardness. Now, this is a convex function. Now, this can be minimized efficiently, right. So, like how SVM deals with the NP hardness using hinge loss, logistic regression deals with this green loss, and this has a name, and this is called as the logistic loss, right. So, this is how logistic regression can be interpreted as dealing with the NP hardness of 0 1 problem, right. So, basically what we are saying is that different algorithms use different convex surrogates to minimize instead of the 0 1 loss, and depending on how good this surrogate is in representing the original 0 1 loss, we get different performances and so on and so forth, right. So, the conclusion that we finally draw using this picture, let me put that down. So, the conclusions here are as follows. So, 0 1 loss is hard to minimize. First point. The second point is different algorithms use different surrogates, surrogate loss. Surrogates are convex and hence easy to minimize. This is the main idea, right. So, this is the reason why we have so many algorithms for classification as opposed to regression, because in regression what we cared about is the squared loss, which is already convex, and so we did not have to look further. Then we did the regularization and so on, right. So, which is a separate point of discussion. Now, here even the loss that we care about is not convex. So, these different surrogates deal with it in different ways, and now of course, in each of these cases you can also do a regularization, right. So, you can, for instance, SVM does this regularization implicitly, right. So, where the goal itself was to maximize margin, which gave us the regularization effect. In logistic regression, implicitly there is no regularization, but in practice you always run logistic regression with the regularization term, right. So, it's as easy as running the logistic regression. I mean, anyway, if you are using gradient based methods to solve it, it's not too hard to solve this. So, this is a high level view. We can put down, for instance, perceptron. We can think of perceptron also in this framework. It won't be as clean as this, but we can do that, and I'll talk a bit about that in a minute. We can also put boosting in this framework. where you will use something called as an exponential loss, right? So let's talk briefly about that before we end this discussion.